before we get into that demonstration, let's take a look at the schedule. Now, this maybe makes it seem more scary than it actually is. Let's look at the schedule in this view. You're kind of going through the gauntlet in this course in that there's just a lot of stuff all at once. And now what I did was I broke the assignments into smaller pieces so that you're doing more frequent assignments but maybe smaller assignments. And let me point out, for example, what that looks like. So you've just turned in Design Project Phase 1, and Homework 8 is due on Friday of this week. It's been posted for a little while. Homework 9 is due on Wednesday the week after spring break, and that's just 2 problems. So it's not anything, 2 or maybe 3. Let me just take a look.
Say there's 2 problems, but it's still going to take like 5 hours.
5 hours? Maybe if you get hit on the head during spring break, or drink a little too much. No. You'll do great. You'll do great. So let's see. Here's Homework 8. I guess I didn't load Homework 9 yet, but I've got it ready to go. But what I wanted to point out to you was that most times, most days from now to the rest of the semester, you're going to have something to submit. So there's a lot going on, and you're going to have to pay special attention to make sure that something doesn't slip through the cracks. I'm going to continue to do the announcements in class, but there's just a lot of stuff between now and the final. So, all right. Friday is Homework 8. Then Wednesday after spring break, Homework 9. And then Friday after spring break is Phase 2 of the project. So you did Phase 1, which is demand estimation. You know how much water is supposed to go out for each one of those arrows in the map, in the network map. So we go to the network map and take a look. You know each one of these green arrows, what's the flow rate during the design condition. I'm going to go through your demand estimation as quickly as I can and give you feedback, but you can begin your design based on the flow rates that you've got now. And then you may need to, further change some of the pipes if I find a significant error in your methodology for the demand estimation. So you know the flow rate, and we just have to figure out, number 1, where should the pipes go? And your objective is to minimize the cost. And so it would be foolish, for example, if you had a separate pipe coming from location A to each one of these arrows. Think about what that would look like. You have A, B, a separate pipe that goes around location B and goes to C, and then AE, AF, AO. I mean, obviously that would be ridiculous. It would be better to have a pipe that connects A to B and then connects B to C, but then to connect C to E, you don't need to follow the perimeter of the city. You can connect them directly. Just go straight from C to E. But there's a lot of different possibilities, and you want to minimize the overall length that you use for pipes, and you also want to minimize the expenditures because you know the cost of each pipe per linear meter. And that data is in the project handout. Let's look at that. The pricing is here, where you find out, for example, every meter of pipe that's 100 millimeters in diameter is $38, $40 for 150 millimeter diameter pipe, and these are the only pipe diameters that you've got available for purposes of the project. So, just to illustrate the next phase of the project, we're going to talk a little bit about that and go through a demo with WaterCAD. So if the pipes aren't big enough, there's problems. The pressure is too low to actually carry the quantity of water that's needed at the design condition, The pressure's too low if the pipes aren't large enough. And so buildings will burn, people won't be able to irrigate. It's just a real negative thing when there's not enough pressure to deliver the water to where it ought to be. And the pipes need to be big enough to carry your design flow rate, which for each location you've either, if it's like one of the external flows, you went through the process of determining what the external flows. If it's the internal areas, then it has to be the maximum hourly demand or maximum daily plus fire. And what we're going to assume is our acceptable range of flow rates is from 240 to 850 kilopascals. And you're going to need to make two different maps for phase 2. You're going to make a map of what your network looks like under the design condition. And so under the design condition, the pressures are going to be relatively low at each of those junctions. You want to get them as close to 240 as you can. Because if you make it so that your pipes are sized such that the pressure at each of the junctions is like 500 kilopascals, it's like you haven't optimized enough. You're leaving the pipes too big because you can get lower than that. The allowable range is down to 240, so your objective is keep making pipes smaller and smaller until as many of your junctions is close to this lower limit as possible. Now under the low flow condition, meaning at night when there's not any demand, for example, you can't have any pressure higher than 850 kilopascal. And what dictates that upper pressure is where you locate the reservoir. Remember on that map, you're going to be putting a reservoir somewhere on the hillside between location A and that spring where the water's coming out. So if you have it really high on the hill, then that pressurizes the pipe network, and you maybe overpressurizes it depending how high on the hill that you put the reservoir. But if it's relatively low on the hillside, then you're not going to have enough pressure in your town to be able to minimize the pipes down. And so that's going to be another part of the iteration process, is figuring out where on the map you put the reservoir, because that's what's driving the water through the pipes. So you want to minimize the pipe diameters, and just for simplicity, you have the ground elevations on that map that I've given you, but you should assume that the pipes are buried. So the elevations I've given you, that's the elevation of the ground, but the pipe itself is going to be under the ground. So what I would do maybe is just assume that the pipe is 1 meter underground at every location. So you've done already this phase 1, which is figuring out how much water is needed. So you're defining the flow rate. And now in phase 2, you're answering the question, what size of the pipe is required? And you're optimizing. You're also figuring out where to put the reservoir in order to pressurize the network. So again, the summary is 240 to 850. If the pipe's too big, that's good for pressure, but it's bad for pricing. And if the pipe's too small, that's good for pricing, but then during the demand condition, you're going to have unacceptably low pressure at your junctions. So we have to find that balance in between. Make the pipes just big enough that you have the minimum pressure available, and have the reservoir high enough on the hill that you're providing plenty of pressure, but not too much pressure. You don't want to have more than 850 under static condition. Static meaning that there's no demand at the junctions. All right, so we're going to do all that with WaterCAD. And in previous semesters, I've used a similar program that's called WaterGems, and actually you can download either. WaterCAD is just a subset of WaterGems. WaterGems has a little bit more sophistication in the analysis of unsteady flows, but we're not going to do that for this project. We don't need all that extra functionality. So WaterCAD is a slightly smaller program. The two operate and look virtually identically. It's just a little bit of extra features with WaterGems. So I might accidentally slip up and occasionally say WaterGems. I mean WaterCAD, WaterGems. It's all basically the same as far as we care. So in this example, this is a similar layout to one that we solved using the spreadsheet method. And I want to show you how we could set this up. First of all, drawing the junctions and inputting all of the data into WaterCAD, and then figuring out what flow rate is going through each of the pipes, calculate what's the pressure at each node, and then I'll show you what I mean by optimization. Are there any more of the handouts?
Yeah.
You got one there? All right. Thank you. I just need it in front of me while I operate the program. So if you've got the program installed already, you're welcome to follow along, and if you don't, that's no problem. Don't worry about it. Just maybe take it in and try and get a sense for what the workflow is. I'm going to create a new hydraulic model, and if it asks me about like tracking changes, I'll just dismiss that because I may have already told it not to ask me again. I don't care to track changes at all. All right. I'm going to lay this out in just a schematic way where it's not on top of a map, but I've showed you before, I think, that you can import the map that's provided here. I go back. Yeah. Here's this scaled map. If you download that, then you can bring it up as a background layer and then draw on top of it within WaterCAD. But for today's example, I'm just going to begin by drawing our reservoir and then some junctions. Let's see, here's A, B, C, D, F, back up to A, and then I've got to have E here, connecting it, and connecting it. All right, that doesn't look, you know, as straight and proper as the handout, but I mean, I think you can see what is what. And I'll take a moment just to rename all of the junctions so that it's consistent with what you've got on the handout. So maybe what you ought to do as far as note taking is just like a bullet point of what I did step by step. So I'm renaming the junctions right now. And you have the similar thing on your project where the junctions, I've given them names, and so your naming convention needs to be the same. So where it says J1, I want that to be called A, B, C, D, F, and E. All right, so the junctions are labeled. I'm going to go here into the tools, and in the options, it's already doing my units in SI, so I'm good there. I do want to go into analysis options, and in the base calculation options, if you double click on that, see how it's saying Hayes and Williams? It'll give me pretty good results with Hayes and Williams, but it'll give me better results if I switch it over to Darcy-Weisbach. So that's another thing that's kind of the preliminaries, checking the units and switching the friction method to Darcy-Weisbach. Okay, so I've adjusted that. Now I need to put in the elevation at each junction. On the handout I've given you, you can see what the elevations are. Elevation at each junction is known, so that's the physical height of the land. Okay, so I'll open up this flex table. It's a way, you know, rather than having to double click on each one of these and open up the properties one by one. I mean, I could put the elevation, the physical elevation of that junction here, but it's just easier, I think, to see it all from the flex tables. And so the elevation at A is 0, B is 9.4, 9.4, C is 19.2, D 25.2, E is 2.1, and F is 5.5. So I've got my physical elevation. Now here where it says demand collection is where I want to specify the flow rate that's going out. So if we look on this map, there's water going out at F, D, and B. So it's in the demand collection that I'm going to specify those quantities. So I'll click on junction B, demand, liter per second, 350 liters per second. And I can close that. So that was defined in B. Also need to put it into D. So here collection for junction D is 100 liters per second. Okay? And then junction F. was 50 liters per second. So I know where the water is going out, and it's going to automatically draw the water from the reservoir. So I don't have to tell it what flow rate is coming from the reservoir. It will just draw as much as needed from the water, from the reservoir to supply the outflow dimension.
You need to do E too.
Did I not do E? Let's see. Junction E. Oh, thank you. E is 450 liters per second. All right, thanks. Okay, so I've got my flow rates. Now I need to go into the pipe properties and make sure that the lengths and the diameters of those pipes match what I know. So for example, I maybe want to rename these pipes. You know, P2, I'm going to call that pipe AB. P3, BC. You can see that I'm just naming them based on the two junctions that they connect. All right, so material ductile iron. No, I don't think I'm using ductile iron. What it says on the handout is that epsilon is 0.3 for all of them. So if I go here and choose in the material libraries, I've got a wide range of materials. Let's just look and see what it's assuming for the ductile iron. It's assuming the roughness height, oh, okay, 0.0003. That actually is the right epsilon for the roughness height. So I'll leave it as ductile iron because that does have the equivalent sand roughness that I need. Diameters though. Okay, pipe AB is diameter 400 millimeters. BC, oh, I'm sorry, that was the pipe from the reservoir to A. And that has a diameter of 1,000 according to the handout. So 1,000, it says meters, it should be millimeters. Diameter 1,000 millimeters. And the other thing I'm going to have to do here is turn on user-defined lengths. Because right now it assumes that the length of the pipe is based on like a scaled length. So let me turn on user-defined lengths for each of these, and I'll put in the diameter and the length of the pipe. Maybe I'll just move where that is. I wonder if I can drag it over. That was easy. Yeah, I can. All right, so it's 10 meters in length. Okay, so pipe AB is 400 millimeters and 220 meters. Pipe BC is 200 millimeters and 100 meters in length. CD is 150 millimeters and 80 meters in length. DF, 300 millimeters and 200 meters in length. AF, 300 and 180. EF, 250 and 80. And now finally, CE has 350 millimeters the diameter and 150 in length. Hopefully I got that right. All right, so it automatically saves. I don't have to like click to save. Anytime you type an entry, it saves. But speaking of which, let me show you what kind of files it creates. So I'm going to do save as. I'm going to create a special folder where I save all this stuff, just so you can be aware that it's going to create more than a single file. WaterCAD demo. I'm calling this in class. And then if we go over here to that folder where I just saved the files, you'll notice so far I've already got 3 files. And I couldn't open this unless all 3 of them are present. So it's not just this one that has to be there, but this database file is where all the characteristics of the pipe are being saved as well. So just be aware that if you want to move your files from one computer to the next, you have to copy over the entire folder that you save these files in.
Is the DWH a drawing?
Yeah, it is. Yeah. Okay. So I think I've defined everything I need to. It knows the length of the pipe, the roughness, knows the elevations. Oh, I didn't say the elevation of the reservoir yet. So let me open up the flex table for the reservoir and tell it that the water is at an elevation of 65 meters. Okay. Now I'm going to click this green compute button, and hopefully we don't get any error messages. Green is good. It knows the total flow rate that's going to be drawn from that reservoir is 950 because of all the demands that we specified. What we can do is, if we open up the flex table, we can see what's the flow rate through each pipe. So if we open up the flex table and look at the pipe, you can see liters per second that's going through each one of those. So for example, from the reservoir to junction A is 950 liters per second. Why do you suppose some of these flow rates are listed as negative? What do you think that has to deal with?
Backflow.
It's not backflow, although that's a reasonable guess.
Or is that where it defines the loops?
Yeah, exactly. Yeah, it's the direction of flow. So clockwise is positive, you know, because it's using that same technique in the background, the Hardy-Cross method that we used with spreadsheets. So flow rates, don't be thrown off if it gives you a negative flow rate, because in the case of pipe CE, for example, it just means that when you're in the context of this loop, that the flow is against the clockwise positive direction. You notice it's putting these little drawings, the little arrows that shows the direction. Well, we can annotate the drawing with the flow rate. I think I've showed you this before, how over on the left side you'd right-click on the pipe, new annotation, and then we could choose from the drop-down box and have flow. Oh, I clicked the wrong one. Flow absolute maybe would be a good one, because then it's not going to have the negative. Let's do flow absolute. So Q equals, and I'm going to offset it above the line with a positive Y offset of 4. So Q equals, for example, 528. So now we can see how much flow is going through each one of those pipes. And it gives you a default location, but if you don't like where it sets it, you can always click on the individual annotation and move it, you know, if it's dropped it on top of something. What about the real thing that we're trying to do is make sure that the pressures every place are all right. So let me put in the pressures. So annotate the junctions with pressure. I'll have that P equals, I'm putting a prefix on there just so that, I don't know, it would be obvious it was talking about a pressure because it gives you the units, but I like it better that way. So I'll do a negative X offset, -5, and the Y offset I'll do negative as well. And then apply that. All right, so check out our pressures. What's the lower limit? 240. So we already are below the lower limit here at junction D. I guess I could annotate. I don't know why I don't see junction D. Maybe the annotation is over here. But see how that pressure is too low? So that means I need to make pipe DF bigger. Do you see the direction of the flow? That means that the pressure provided at junction D is a result of the diameter of pipe DF. And the pressure at F is 370. So I've got a few different options. If I make AF a bigger pipe, then it's going to increase the pressure at F and at D. But if I make FD bigger, then it's going to increase just only the pressure at D. They're the same diameter right now. AF is 300 millimeters and DF is 300 millimeters. So this is the shorter pipe. Let me just see if I increase the diameter there from 300 to 350, whether that would get me into the acceptable range at location D. Probably not. let's just execute the model again. It got me, what was the lower limit? 240? We're there, 247. So it looks like every place is good now. Each one of these junctions is within the limit. So could we further optimize? Look at pipe AB. We might be able to knock down that pipe. Certainly we could make EF or CE lower because 409, that's more pressure than we need at E. So let's say this pipe CE, which right now is 350 millimeters. Well, let me just annotate, by the way. It's easier to do this optimization if we have the pipe diameters annotated. So let me annotate diameter, and I'll have D equals, and we'll do it below the pipe with a negative Y offset of 5. All right. So see how that's 350? I'm going to make it smaller. So let me go into the pipe table, and let's have CE. Instead of 350, let's bump that down to 300. Execute the model. And the pressure is a little bit lower at E, but not much. It went from 409 to 401. So we hardly lost any pressure at all. And we made that pipe smaller, so we've just saved our client probably thousands of dollars with that one little optimization. We could take it further. Maybe we could see if 250 is good enough. 250, execute. So the optimization process is what you're going to spend a little bit of time on for the project. Yeah, we got away with it. 381. We might be able to go a little bit smaller. Looking at the flow rates, see how you've got 289 going through this pipe, but only 161 going through this one? They're both the same diameter, but there's less flow going through CE. So that's the one. That's why I'm playing around with CE. Is I think that I can get away with making those changes. So optimization is I want you to try and get your network as close to ideal as possible, where this would be your peak demand type map. You're going to have an annotated map for the design condition where there's a lot of flow rate. Then you have to do another map for what does it look like when there's no flow rate. So I'm going to save this file, and then I'm going to go to my junctions and turn all the demands down to 0. So all the demand collection down to 0. Let me just delete that. No demand there. Delete the demand here. And let's find out what does this network look like under static conditions. Okay, I think I've turned off now with this one all of the flow rates in the network. Compute the model. Now we should just have the static. See how the flow rates are 0, 0, 0, 0? So this is the static pressure. And what this tells me is none of them is close to the 850 limit. So if I had the option, I'd move the reservoir higher up the hill, because the more pressure you've got under the static condition, that's going to give you more headroom to work with as you're reducing the pipe diameter. And this is a super important point. It seems like half the students in the class don't fully appreciate this relationship, that you want to have the reservoir as high on the hill as you can get away with, because that's like your currency for optimization. That's where your pressure comes from. And the more pressure you've got under the static condition means you're going to have more pressure under the demand condition, and you can make the pipe smaller and smaller and smaller. So since none of my junctions are yet near that upper limit of 850, then I'd move this reservoir higher and increase the elevation of it. So in a nutshell, that's what you're going to spend most of your time doing in phase 2. Are there any questions about either WaterCAD in particular or the project more generally?
On the flex tables for the pipes,
yep.
We define one of the lengths for the pipe and overlay it onto the map. Would that allow us to, or would that allow it to calculate the rest of the pipe lengths automatically?
Let me show you specifically that. You've got the right idea. So I'm going to download this scaled map. This is important because there's an error that you might get. So I'm going to just download. Depending on what browser you use, you may have to right-click and save as. Otherwise, it'll just show you the picture. But in my case, it has downloaded it to the downloads. All right. So I'm going to save this model and then have a fresh one. Okay. I'm going to bring in the background layer, new file, and browse to that picture I just downloaded. And I want the compression. I think I want to turn off use compression. It's either off or on. If I got an error message, it's because it needs to be on. Okay, so turn off compression. All right. Okay, so it's showing me the thing. So if I draw, this is how you know that it came in correctly. See right here, this line should be 100 meters. So I'm going to draw a pipe on top of that. And if the pipe is 100 meters long, then that tells me that this scaling is correct. So I'm going to drop one of the junctions there and another one there. Okay, now let me double click on that and it'll tell me the length of that pipe. Length, 100 meters. Okay, so now that I've got that, I zoom to extents. I can draw, like, here's my reservoir. I'll put my reservoir halfway up the hill. Okay, so here's the reservoir. Now I'm going to do the junction. Here's a junction. There's a junction. Here's one down to E. Okay, and I can turn this on and off. So when I'm ready to do my maps, they're small, but now I think your question was, in the flex tables, are the pipes the correct length? And now they are, because I drew them on top of that scaled map. So here, length, 830, 665, 665. It still has that first pipe that I drew, this one that was 100 meters. But like these lengths, we no longer have to do the has user-defined length thing because the scaled lengths are correct. All right. But one thing, notice how since the pipes are really long, you may notice that you can't actually see the symbols like that are at the end of it. So here under Tools, I'm giving a tour to a prospective student, and I guess I'm probably getting a lot of calls from that. Okay, so go to Drawing. Right now, the symbols are pretty small, so symbol size multiplier, let's do like 5, and for the text as well. Like if your annotations are too small, that's still too small. So let me go back here into the options. Oh, where was it? Yeah. Symbol size multiplier 10. And text multiplier 10. And they're still pretty small, but I mean basically this is the tool that will allow you to change how big the little symbols are and your annotation if it turns out that they are too small. All right. That's probably all the time I've got to show you WaterCAD, but you should begin exploring with it. Remember that we do have more class. I just want to make the point that you've got a couple of homework assignments between now and Phase 2, but you're going to have to work in parallel on those things. All right, open channel flow. Our book in the discussion on specific energy makes the point that specific energy is both the depth of flow and the velocity head. Do you remember what Manning's equation predicts? When you solve for y using Manning's equation, what is it assuming about the type of flow that you've got? Uniform flow, that's half of it. That's right. Uniform means that there's no change in flow with respect to position. So Manning's equation assumes uniform flow and what else? Steady flow. Good. Most of the time, water isn't steady and uniform. So we need some other ways to predict what the flow depth is going to be. Last week we solved for y in a trapezoidal channel using Manning's equation a couple of times. And that formula will only give you the correct depth if you've got a really long stretch of channel where there haven't been any disturbances to flow. But if you've got a river where the slope is always changing, and if you've got a river that's meandering and changing direction, then you're not going to have steady uniform flow. So what we're talking about now is some of the tools and techniques we can use to predict the depth when conditions aren't steady and uniform. So specific energy analysis is one of those tools, where what we'll do is we'll look at how much energy is there at one location in the water, and we know that downstream there should be the same amount of energy, or the same amount of energy minus losses. So specific energy analysis begins by just quantifying how much energy is there. And so the specific energy is saying relative to the bottom of the channel, where you're using whatever the base of the channel is as your datum for measuring energy, then how much energy is there in the flow? There's the depth and the velocity head. And of course, sometimes it's more convenient, instead of expressing velocity head in terms of v, we can express it in terms of q. So q squared divided by 2ga squared, that's the same as this velocity head. Now, in a rectangular channel like this, it's 4 meters wide, and let's say it's carrying a flow rate of 10 cubic meters per second. Well, it could be shallow and steep, meaning that the velocity is really fast, or the water could be really deep and slow moving, like if the slope was relatively mild. If it was an easygoing slope, in a place like Florida where there's not a lot of hills, the slopes are really flat there and the water's moving slowly. So how many different ways can 10 cubic meters per second go through a rectangular channel? Well, just to illustrate, let's say that we have a flow rate of 10 cubic meters per second, and I'm choosing a lot of different flow velocities, just to illustrate that there's many combinations of velocity and area that will give you a flow rate of 10 cubic meters per second. So if you know that Q equals VA, if the velocity is 10, the area would have to be 1, right? And if the area is 1 and the channel is 4 meters wide, then that would tell you what the depth has to be. So there happens to be a shallow depth where the velocity is moving very fast. Think about if it was a really steep channel. You could get 10 meters per second, 10 cubic meters per second with a relatively shallow depth if it's steep. But if that same 4 meter wide channel is carrying 10 meters per second, 10 cubic meters per second on a shallow slope with a low velocity, then the depth would have to be much taller. So this last column is the specific energy. And so what we're calculating is how much energy is there in the flow when you take into account the depth plus the velocity head. And so velocity head here, q squared divided by 2ga squared. Okay, so this is showing, I'll just remove this. Typically, if we had more time, then I'd have you calculate the area, depth, and specific energy for these ones with the green arrow, just so that you get the practice of how to calculate the specific energy. But the broader fundamental point is that there happens to be some depth that minimizes the specific energy. So look, this is the lowest, E. You've got a lot of energy at this extreme because the water's moving so fast. There's not very much energy in the depth. Most of the energy is velocity head when you've got this extremely shallow, fast-moving flow. If you have this deep, slow-moving flow, most of the energy exists as the depth. Look, the total energy is 2.551 meters, and 2.5 of that came from the depth. And so only a small fraction of the energy is the velocity head. But what is going on with this minimum specific energy? This is a critical point. And this is actually what we call the critical depth. And it's a special It's a special point on a curve that we sometimes draw. This is a boring curve that's not really important. You won't see again flow depth versus flow velocity. But this is a really important curve that you'll see lots of times, and you're going to make this curve because there's a lot of things we can learn from this. It predicts what the velocity and depth is going to be downstream when some change occurs to the channel. Like when you put obstructions in the way of the water and the water changes, this curve is going to predict what happens to the depth because of the obstruction that you've put into the flow path. So let's look at what this is. On the horizontal axis is the specific energy, which is just a graph of depth versus depth plus velocity head. So specific energy, and then here is the depth of flow. So remember on this previous curve where we pointed out this is the lowest specific energy, on the graph, that's this point. Furthest to the left on the curve. Minimum specific energy. And what it corresponds to is the critical depth. Do you remember earlier you classified flow as either subcritical or supercritical? With the Froude number. Did we do that in fluid mechanics? Froude number? Was this class? Yeah. You had a homework assignment where you flow regime. You classified the flow regime. Okay. Well, anything that is below this critical depth line is supercritical flow, and anything that's above it is subcritical flow. Because the region of the graph that's above this dashed line corresponds to deep flow with a slow velocity. And then below this line is fast-moving water with a high velocity but a shallow depth. So minimum energy corresponds to the critical depth. What controls the depth that the water is actually flowing at is the slope of the channel, how steep it is. Remember, it can flow at any combination of depth, velocity, for a given channel, width, and flow rate. So how deep the water is going to be is just how steep the channel. The roughness of the channel also contributes, but for a given section, it's the slope that determines the depth. Now, alternate depths are two depths that have the same specific energy. So let's say you have a specific energy of 2 meters. There could be a depth of, it looks like about 0.5 meters, or if we go up here and find the crossing point up above in the subcritical region, the depth looks like it's about 1.7 meters. So 1.7 meters has a specific energy of 2, and 0.5 meters has a specific energy of 2. They have the same amount of specific energy, so they're alternate depths. Let's go back to this table, this one. Can you see any depths from the data that's given? Can you see any that are pretty close to being alternate depths? Here we have 1.44 meters, and here's 1.45. So it looks like that a depth of 1.25 and a depth of 0.625 are approximately alternate depths because they have the same specific energy. All right, so classifying the critical flow, you look at the Froude number or the depth to determine whether the flow is subcritical versus supercritical. And so when the depth is more than the critical depth, the flow is subcritical. And the reason why it's sub is because the velocity is low, which leads to a low Froude number. And if the depth is less than the critical depth, the flow is supercritical because the water velocity is fast. There is a parameter, uppercase B, that refers to the top width of a channel. And when the channel is flowing at its critical depth, then whatever top width you've got, we call that as the critical channel width. So capital B sub C. So if it's a rectangular channel, then capital B and lowercase b are the same, where lowercase b is the bottom of the channel width. But if it is a rectangular channel, if it's a trapezoidal channel, then the top width depends on how deep the water is and the side slope. Now the reason why I've been mentioning the top width is that that's one of the parameters that you use to calculate Froude number. So when Froude number is greater than 1, it's supercritical, and when Froude number is less than 1, that's subcritical. So the way that you can diagnose critical flow, there's a couple of ways. One is you could compare the depth to the critical depth if you know the critical depth. But if you don't yet know the critical depth, another way to determine whether you've got supercritical or subcritical flow is to calculate the Froude number. So this is the Froude number squared on the left-hand side. So then the Froude number itself would be the square root of the flow rate squared times the top width divided by G times A. So classifying critical flow is the same as diagnosing the flow regime from that earlier homework assignment where I asked you to figure out the flow regime, whether it's supercritical or subcritical. Froude number can tell you that. There's this parameter known as hydraulic depth, which is the ratio of the area of the channel to the top width. So here's the formula for a hydraulic depth. It's the area divided by the top width. And for a rectangular channel, if it's very wide, a really wide channel, and by this phrase very wide actually has a technical definition. A channel that's very wide is 20 times or more wider than it is deep. That's what I mean by very wide. So if a channel is very wide, then the hydraulic depth is the same as the physical depth, regardless of what its actual shape is. So here's a very wide channel. And the hydraulic depth of a rectangular channel, remember, it's just the physical depth. So with the 2 minutes that we've got left, let me just show you how we would calculate whether a depth of 0.25 is supercritical or subcritical. Number one, we could look at the figure, the specific energy diagram, and we know that the critical depth on this figure is 0.86. And so if the depth is less than the critical depth, then that tells us it's supercritical. That's why it's bold. If we calculated it based on Froude number, we could do it that way as well. Since the Froude number is greater than 1, supercritical. And for this depth, which is more than 0.86, which is our critical depth, that makes it a subcritical, and it's also verified with the Froude number, being less than 1. Can't believe we got through all the slides. All right. Well, it's 1:49. We are out of time. We'll get together on Wednesday and continue talking about specific energy. Hope you have a good day.